Hey everybody, Professor Tomney from Chem Complete here. We're going to work on a significant figure lecture in just a moment, but I wanted to let people know if they come over to chemcomplete.com and you create a user account, you can go to the free resource page, and on this page we have a free significant figure guide that is available for download. It will cover everything that we go over plus a little bit more, and it will have a set of practice problems as well as a worked answer key that you can get a hold of to test yourself. So with that, let's go ahead and begin the lecture. All right, so we are going to talk about significant figures, which is one of the first topics that tends to come up in a generalized chemistry course, particularly when you get into labs and you have to start dealing with measurements. So we're going to give a little bit of brief background and define some terms, and then the main goal of this first lecture is going to be to discuss how do you determine the number of significant figures when you are presented with a value or a measurement. Now we will have an additional lecture that goes into the mathematics and the order of operations. So in other words, when I add and subtract significant figures, how do I determine the number in the answer? Same with multiplication and division, and so on and so forth. All right, so what are significant figures? When we start talking about these, a significant figure is basically going to be any single numerical digit used to express the required degree of accuracy and precision for a given measurement. And these are typically going to be numbers 1 through 9. Now, 0 is where we're really going to have a question. So any number 1 through 9 will always be considered significant, and we'll see that in the rules in a few minutes. But 0 usually leaves some question, and we have to have some additional rules to determine if zeros are going to be counted as a significant figure or not. So all significant figures must begin with a non-zero digit. So when I get ready to start looking at a significant value, for instance, let's say that I have measured something on a scale in a laboratory and I find 52.03 grams, right? The first digit here is a 5. It's a non-zero digit. Okay, so if I had something, for instance, like this that began with a bunch of zeros and then I had 5203, I wouldn't begin significance until I get to my first non-zero digit. And again, we're going to outline some rules for this in a few minutes. All right. Now, why are significant figures important? They're important because instruments and devices like the scale we just talked about are used to make measurements, and those measurements are going to have limitations when we start talking about error and working in the lab. And this is sometimes referred to as the degree of uncertainty, which we'll discuss in just a second here. Right? So when an observer wishes to express the certainty or uncertainty of a given value that they have observed in the lab, significant figures are used to communicate these parameters to other individuals that will be looking at the data. So for instance, let's say the scale that we used in this example has a plus or minus 0.01 grams. Well, in that case, we're saying if the scale says 52.03 grams, this is the degree of uncertainty that is found in this measurement, because it could be anywhere between 52.02 to 52.04. So anytime we see this last digit, that's called the digit of uncertainty, or the measurement of uncertainty, the degree of uncertainty, etc. And that is where we cut off our significant figures. So the last significant figure in a value will always be considered the degree of uncertainty when we're looking at measurements. All right, so a couple terms came up that we're just going to briefly discuss here, and those include accuracy, precision, and degree of uncertainty or error uncertainty. All right. So accuracy, and these definitions are all in the free guide. They're written out there. Okay. Accuracy is the degree to which an observed measurement is going to align with an accepted value in the scientific community. So for instance, most people agree in the scientific community that, for instance, the acceleration of gravity due to Earth is 9.8 meters per second squared. Now you can get into more detail. I'm not a physicist, but it probably goes several significant figures out past that. However, if you were to run a trial and you were to, let's do a free ball drop or something like that in a lab, and you were to measure the acceleration, how accurate you are is how close you get to this accepted value. Now, sometimes when we're doing research, we're in discovery mode. We're looking for new values, things that have not been determined yet. And in that case, it's very difficult. You're not going to be able to tell whether you're accurate or not because you are sort of laying the groundwork. And other people, through the scientific method, would need to repeat the process, confirm your results, and if enough people start to gather that evidence, you start to develop a theory which can become a law, and then that is held as the standard, at which point we look at, how accurate are you relative to that standard. Now, precision is the degree of certainty and specification in an observed measurement, and that is what we express with significant figures and digits, okay, particularly when we are doing repeated measurements of the same value, right? So again, going back to that scale example where I had 52.03, the question is, if I continuously take a measurement on that scale with the same amount of material, how often do I come up with 52.03? And how precise can it get? So in this case, it can go to the hundredths place. Maybe there's another scale that could go 52.03006, right? So the level of precision is greater in a situation like that, provided that the repeated measurements are coming up the same. So significant figures help to communicate how precise those values are. All right, and then degree of uncertainty, like we had discussed earlier, this is going to be the point, or specifically the digit, at which an observed measurement is subject to some level of error, and it's usually going to be the last digit reported in a set of values. So it'll be plus or minus some value, and that is where your uncertainty will lie. Now, sometimes that's going to be a digit that's reported to you, like on a balance, a digital balance. Sometimes you may be making that estimate. So if you're looking at the meniscus, right? So let's say that I've got something like a graduated cylinder here, and this says 50, and then it goes up to 51, and then it goes up to 52, and the meniscus is right in between here. You're making your best estimate and say maybe this is 51 point, and you know exactly where 51 is, but you only have the liberty to take one additional value, 51.3, let's say, right? Because we're uncertain where it falls between 51 and 52, which are the clear markings. So this becomes the degree of uncertainty where you as the user are saying, I am uncertain about how much further it goes beyond this. This 3 is my best estimate. That's where my uncertainty lies. Okay, so that's an important concept as you're working through the lab. So there's several rules that help us when we're dealing with significant figures and determining, when we look at a value, whether something is a significant digit or not. So they're pretty straightforward, okay? All but one of the rules is going to give a very clear answer. Either something is significant or it's not. And there will be one rule that leaves some ambiguity that we'll talk about. That'll be the last rule. Okay, and then once we're done with that, we're also going to look at some cases where we have discrete counted objects and exact conversions, because those are special cases. All right, so let's go ahead and start talking about the rules here. All right, so rule number 1 is that all non-zero digits will always be significant. This is an easy rule. It's not one that is overcomplicated, right? So anything 1 through 9 will always be significant no matter what. So if I give you 5,236.72, you have 1, 2, 3, 4, 5, 6 sig figs in an example like that, because any time, under any circumstance that you have a number that is not 0, it is going to be considered a significant digit. All right. Now, rule 2. All zeros between two non-zero digits are considered significant. Again, this one's pretty easy. So what this is saying is, let's say things like 101 or 5,002 or 1,378. These zeros that you see in between two non-zero digits will always be considered significant. So now we're starting to get into the territory of dealing with the zeros, and you'll see the rest of these all deal with zeros, because 1 through 9 is very cut and dry, and then the zeros is where we have to make some determinations. All right, rule 3. any zeros preceding, meaning coming before, the first non-zero digit are not considered significant. So this is when we start usually having very small values, right? And we had an example like this to begin with, right? All of these zeros, because they come before the first non-zero digit, these would not be significant. So I would only have 4 sig figs in an example like this, right? So anytime you see these, what's essentially called placeholders that come before the first value, those are not going to be considered significant, right? Rule 4, any zeros that come after a non-zero digit, and this is important, with a decimal present, are going to be considered significant. So if I have 100.0, all 3 of these zeros are considered significant, and I would have a total of 4 sig figs. If I have 723.000, all 3 of these are considered significant, okay? And I would have a total of 6 sig figs in an example like this. All right, so again, any zeros that come after a non-zero digit, so you see we have a non-zero digit first, these zeros come after that, and a decimal point is present, you see it. And this can even be when you have something like this, 6,000 with a decimal and there's no zero after it. These would still be considered significant in a case like that, okay? Now, the decimal is important because in Rule 5, any zeros that come after a non-zero digit without a decimal present are ambiguous. So this is the rule in which we're not going to have a clear determination. So if you say something like 1,000 and there's no decimal point, okay, this would have at least 1 sig fig. It could be 2, it could be 3, or it could be 4. We know it's at least 1, but it could be 2, 3, or 4. Okay. Now, if I have something like this, 5,760, right? In this case, I know I at least have 3. I wouldn't say maybe 1, maybe 2, maybe 3, because all the non-zero digits are significant. So it's 3 or 4. We're not really sure there. All right. So the lack of decimal is going to make it ambiguous. Now, there are certain cases where we're going to have an infinite number of sig figs. And these are the 2 sort of exceptions that we have here when we're dealing with this. All right, now the first example is when you have a discrete number of counted objects. Okay, and when we use the term discrete, that's exactly what we mean. That you can discretely count the individual objects. So for instance, if I pick up a dozen donuts, I have 12 donuts, right? And if I say I have 3 dogs at home, I have 3 dogs. I can count each one of the dogs, right? When a scale turns around and tells you 53.02 grams, you can't count each of those individual grams. It is doing its best to estimate the number of grams in the object that you are measuring. It's a measurement. When I take and I count these, this is not so much a measurement as I'm counting objects. So another way to understand this is, let's say that I have something like 3 dogs. That is the same as saying I have 3.0 dogs. I have 3.00 dogs. I have 3.000000, and you can go on into infinity, right? Because it's not going to change. I can't all of a sudden have 3.000001 dogs. There's no such thing as 1, whatever that is, billionth of a dog, right? It has to be a whole counted object. And because of that, there is technically an infinite number of zeros that can come after a discretely counted object. And it falls into the concept of an infinite number of significant figures. It's not really subject to significant figures at that point. Okay? And when we have these types of situations, we do not count them towards the mathematics of sig figs. So when you get into, okay, I'm about to multiply this sig fig by that sig fig, if one of them is a discrete value, it is exempt from the consideration because you're obviously not going to report an infinite number of significant figures. Right? So the second one is whenever we have some type of conversion. And conversion we're talking about in the scientific sense, right? So 1 inch is going to be equal to 2.54 centimeters. So some students are tempted to say, oh, 2.54 centimeters, that's 3 significant figures because there are 3 non-zero digits. Well, the problem with that is that this again falls into, similar to the first example of a discrete value, this is by definition 1 inch. So what we're saying here is 1 inch, so 1,000,000, right, into infinity inches, is equal to exactly 2.54, okay, 0.00000 centimeters. So by definition, 1 inch is equal to 2.54 centimeters. Right? So anytime you start dealing with these direct conversions, that's an accepted value, those are going to have an infinite number of significant figures. Now you have to be careful. If you measured something in lab to be, let's say that you had, I don't know, a piece of string that you had to measure in lab, and you measured with a ruler that it was 2.54 inches, that, or 2.54 centimeters, that is not subject to this, because you are making your best measurement of the piece of that string based on the ruler that you have at hand. So that is subject to significant figures. But let's say that you measure that it's 1 inch, and then you want to convert that into centimeters. This would not be considered in the conversion process to be subject to significant figures. Right? So that one's a little tricky for some students, but the more you practice, you'll get the hang of it. If you're looking at a direct conversion, okay, you are going to be using an infinite number of significant figures, and this becomes important when we're dealing with the math, because we have to choose how many significant figures are present in the answer, and these types of things become exempt because we don't have an infinite amount of digits in our answer. So that covers significant figures for part 1, and what is a significant figure, how do I determine the number, okay? Please like if you found the video was helpful in teaching you about significant figures, and as always, if you comment, we will communicate and try to get back to you. If you subscribe and hit the little bell, you will be up to date as we are releasing content throughout the semester so that you can ace your studies. And again, head on over to ChemComplete and sign up for a free account, because you will get this guide. So you don't have to sit and take notes. You'll have it as a reference, and there are some practice problems out there. So I will see everybody for the next lecture, and best of luck with your studies, guys.